गुड मॉर्निंग स्टूडेंट्स। एमएससी फाइनल पेपर 5 में हमने अभी तक जो फर्स्ट लेक्चर दिया था उसमें एल्कीन्स के रिडक्शन के बारे में बात की थी। इन दिस सेकेंड लेक्चर वी आर गोइंग टू टॉक अबाउट रिडक्शन ऑफ एल्काइन्स एंड रिडक्शन ऑफ एरोमेटिक रिंग। लेट्स स्टार्ट विद रिडक्शन ऑफ एल्काइन्स। There are a few methods through which we can carry out reduction of alkynes. Let's start with the first method, which is catalytic hydrogenation. Catalytic hydrogenation means that we react the reactant with hydrogen in presence of some catalyst. Alkynes undergo catalytic hydrogenation. We get the product alkane in two steps. The first addition of hydrogen gives an alkene and the second addition of hydrogen gives an alkane. You can see here we starts with an alkyne, and in the first step we get alkene and then a second molecule of hydrogen is added in presence of catalyst and we get the final product which is an alkane. The catalyst in this reaction can be heterogeneous or homogeneous. This is again an example of hydrogenation, catalytic hydrogenation. We are using different catalyst here and the end product is formation of alkane. The utility of catalytic hydrogenation is that we can stop the reaction at the first step only and produce alkene as the product. This reduction is called partial reduction of alkyne. The best method to carry out the partial reduction of alkyne to alkene is heterogeneous hydrogenation using Lindlar's catalyst. Now, what is a Lindlar's catalyst? Lindlar's catalyst is palladium that has been poisoned with lead 2 and an amine. The amine can be quinoline or pyridine. The beauty of this catalyst is that it is ineffective for alkene. In the presence of Lindlar's catalyst, non-terminal alkyne convert into cis-alkene. This catalytic hydrogenation of alkyne is one of the best ways to prepare cis-alkene. This is an example of partial reduction of alkynes using Lindlar's catalyst. This is an alkyne and we are using Lindlar's catalyst and the product here is cis-4-octene and the product we get is in very good yield and we get 95% of the product using Lindlar's catalyst. This reduction in the presence of Lindlar catalyst is an stereoselective reaction as we get almost 100% yield of the cis product. Another alternate catalyst to carry out this cis reduction is nickel boride. This is an example of reduction of alkyne in presence of nickel boride. Here again we get 99.5% of the cis product. The next one is reduction with borane. This is called hydroboration of alkynes. In this reaction we use a sterically hindered dialkyl borane to react with alkyne to give vinyl borane. This reaction is again stereoselective and the addition is syn. This vinyl derivative on protonolysis gives cis-alkene. This protonolysis of vinyl derivative is carried out with boiling acetic acid. The reagent is inert towards some of the groups and if these groups are present in the alkyne then they are left untouched and we get only the partial reduced product of alkyne. This is the example of hydroboration of alkyne. In the first step, this alkyne is reduced in presence of this sterically hindered dialkyl borane, that is diacetyl borane, and we get a syn addition vinyl derivative. This vinyl derivative is then made to undergo protonolysis by boiling with acetic acid, and we get a cis product, cis alkene. I just said that this reagent is inert towards some of the functional groups, and if these functional groups are present along with the triple bond, then these functional groups are not undergo any reduction, and only the triple bond undergoes reduction, partial reduction, and we get an alkene as the product, a cis alkene as the product. In this example, along with a triple bond, COO bond is also present in the compound, but this group is not touched, and only the triple bond undergoes partial reduction, and we get an alkene as the product. Alkynes can also be reduced to cis alkene with diisobutyl aluminium hydride. The reduction with this reagent is carried out in inert atmosphere at 40 degrees centigrade. This reagent is again a selective one because it also is inert for most of the functional groups. So we can safely use this reagent, that is diisobutyl aluminium hydride, if some other functional groups are also present in the compound. अगर हम चाहते हैं कि उन फंक्शनल ग्रुप्स पे रिडक्शन का कोई भी असर ना पड़े, तो हमें सेलेक्टिव रिएजेंट्स को यूज़ करना होगा. अभी इस एग्जाम्पल में मैंने आपको बताया कि डाई बोरेन को हम यूज़ कर सकते हैं सेलेक्टिव रिडक्शन के लिए, और डाई आइसोब्यूटाइल एल्यूमिनियम हाइड्राइड इसे भी हम यूज़ कर सकते हैं एल्काइंस के सेलेक्टिव रिडक्शन के लिए, जब दूसरे फंक्शनल ग्रुप्स भी रिएक्टेंट के अंदर प्रेजेंट हो. The third way to carry out the reduction of alkynes is reduction with group first A metals in liquid ammonia. Reduction with first A metal in liquid ammonia. Reaction of a non-terminal alkyne with a solution of an alkali metal. This alkali metal is usually sodium, lithium or potassium, and it is dissolved in liquid ammonia to give a trans alkene. In the first two methods of reduction, that is catalytic hydrogenation and reduction with borane, we get preferentially the cis product, the cis alkene. But here in this third method of reduction, that is reduction with 1A metal in liquid ammonia, we get trans alkenes as the product. This is the first example of reduction with metals in liquid ammonia. See, this is the reactant alkyne, and we reduced it with sodium, which is dissolved in liquid ammonia, and the product is trans alkene, and it comes in very good yield. Approximately 97% of trans alkene we produced in this reaction. Comes to the mechanism part of this reaction. The mechanism of reduction with sodium or 1A group metals in liquid ammonia proceeds via addition of an electron to the alkyne in the first step, and this addition of an electron to the alkyne form a radical anion. This radical anion adopts a trans geometry. The radical anion is such a strong base that it readily removes a proton from ammonia to give vinylic radical. In the next step, the vinylic radical picks up another electron from the metal to give a vinyl anion. Again, this vinyl anion abstract a proton to give trans alkene. We have read about this type of reduction in alkene also, but ordinary alkene do not react with the solvated electrons and the reaction stops at the alkene step, and further reduction of alkene to alkane does not take place in this type of reduction, because we need alkenes in which electron withdrawing groups are attached at the olefinic carbon to undergo this reduction to produce alkane. So ordinary alkenes do not undergo reduction with solvated electron, and the reaction stops at the trans alkene stage. Let's see the mechanism. In the first step, the sodium is solvated in liquid ammonia, and an electron from sodium forms a solution with liquid ammonia. It is a blue colored solution. In the next step, this is the alkyne. It undergoes homolytic fission and it abstracts an electron from this solvated solution, and we get a radical anion, and this adopts a trans geometry. In the next step, since this radical anion is a very strong base, so it readily abstracts a proton from ammonia, and a hydrogen is attached to this carbon. This is vinyl radical. This vinyl radical again abstracts an electron from sodium and it gives anion, and this anion takes up a proton from ammonia and we get the trans alkene. Next, we will talk about reduction of aromatic rings. The first method to carry out reduction of aromatic rings is catalytic hydrogenation. Catalytic hydrogenation is reaction of hydrogen with aromatic compounds, aromatic rings, in presence of catalyst, and the product is the total reduced product of aromatic ring. Means all the double bonds of the aromatic ring get reduced and we get a totally saturated compound. Reduction of aromatic rings by catalytic hydrogenation is very difficult, because in this type of reaction aromatic stabilization energy is lost. See, the ring is reduced at all the points and we get a saturated ring, a saturated compound, and stabilization energy is lost in this process. So we need more vigorous conditions to carry out this reaction. The conditions that we need depends upon the amount of resonance energy which is lost during the course of reduction. If we reduce naphthalene to tetraline, then this reduction is carried out more readily than reduction of benzene. Benzene is reduced to cyclohexane. Here, resonance energy per benzene ring of naphthalene is 29 kilocalorie per mole, whereas for benzene it is 36 kilocalorie per mole. So more stabilization energy is lost in reduction of benzene. So we need more vigorous conditions to reduce benzene than to reduce naphthalene. The best catalyst for this purpose is either platinum, rhodium or ruthenium. These are some of the examples of total reduction of aromatic rings. Benzene is reduced to cyclohexane. This orthopara dimethyl benzene, it is reduced to give, this ring is not here, this ring is not here, this ring is totally reduced Total reduction takes place here also, and we get 1,4-dimethyl cyclohexane as the product. This is benzoic acid, and it is totally reduced to give cyclohexane carboxylic acid. For large scale work, the most convenient method is hydrogenation over nickel. We use nickel as the catalyst at 150 to 200 degrees centigrade and 90 to 200 atmosphere. This is the reduction which is carried out in presence of nickel and hydrogen. In this total reduction of aromatic rings, stereogenic centers are formed. Why this happens? Because as we would expect, one phase of aromatic ring to be absorbed onto the metal surface. The addition of hydrogen is to come from the metal. So we would predict that cis distereomers would be formed preferentially. Now what is a stereogenic center? A stereogenic center is any atom for which exchange of two groups create a different stereoisomer. This is indeed the case, although the level of stereoselectivity is not always high. This is the example of formation of stereogenic centers. When we reduce this compound using ruthenium and hydrogen, we get 90% cis product. And is this 1,2,3 tricarboxylic acid, we get 95% cis product. And this is the stereogenic center, which is formed when substituted aromatic compounds are reduced by hydrogenation. Aromatic rings generally do not give partial reduction in the presence of heterogeneous catalyst, as we have seen in alkynes. Aromatic rings get totally reduced and we get saturated compound as the product. And in alkyne we have seen that reduction at alkene stage, the reaction is stopped at the alkene stage and we do not get alkane as the product. The second method of reduction of aromatic ring is reduction by electron transfer reagent. This is called the Birch reduction, and it is particularly useful and unique in its ability to accomplish the partial reduction of aromatic ring. In the first method, that is catalytic hydrogenation, we have seen that total reduction of aromatic rings occur. But if we reduce the aromatic ring using Birch reduction, then partial reduction of aromatic rings takes place. Electrons are the reducing agent, and these electrons come from group 1A metals like sodium, lithium or potassium, which is dissolved in liquid ammonia. When aromatic rings are reduced by lithium in liquid ammonia, usually in presence of an alcohol, then 1,4 addition of hydrogen takes place and non-conjugated cyclohexadiene are produced. Look here, we are reducing aromatic ring using electron transfer reagent, and this electron transfer reagent is group 1A metals dissolved in liquid ammonia in presence of alcohol. Here partial reduction takes place. In catalytic hydrogenation, if we have been used the catalytic hydrogenation here, then this total reduction of aromatic ring would have occurred, but here only partial reduction takes place and we get 1,4 addition of hydrogen and we produced non-conjugated, this is non-conjugated cyclohexadienes. This is naphthalene. Here again reduction takes place at 1,4 position and we get 1,4-dihydronaphthalene. The mechanism of reduction involves sequential addition of an electron followed by protonation of radical anion species, which is so formed. We have seen it earlier also in when we reduced alkynes and alkenes with electron transfer reagents. In the first step, this electron is dissolved in ammonia and we get a blue colored solution. Let's see the mechanism. Here again, the first step is homolytic fission of double bond and we get radical anion as intermediate. This radical anion undergoes resonance and 3 resonating structures are formed. In the next step, abstraction of proton takes place as we use alcohol in this reaction. Abstraction of proton occurs from alcohol. In the next step, this free radical again abstract an electron from sodium and we get an anion. Again proton abstraction occurs and we get the product, which is 1,4-cyclohexadiene. Formation of a 1,4-cyclohexadiene is quite general in this type of reduction, but the reason for its formation is in preference of the more stable conjugated 1,3-cyclohexadiene is not clearly understood. Till now we have talked about the aromatic ring, but if substituents are present on aromatic ring, then what happens and how the reaction proceed? When substituted aromatic compounds are subjected to Birch reduction, the electron donating groups decrease the rate of the reaction, and this electron donating group are mainly found on the non-reduced position of the product. Let's take the example of anisole. If this compound undergoes Birch reduction, this is an electron donating group. OCH3 is an electron donating group. Then reduction takes place at the position at which this group is attached. This is the minor product. Reduction occurs at the position away from the position at which this group is attached. This is the major product. So electron donating groups are found on the non-reduced position of the product. These two are the reduced position, and this is the non-reduced position at which the electron donating group is attached, and this one is the minor product. On the other hand, if electron withdrawing groups are present in the aromatic ring, then this presence of electron withdrawing group increases the reaction rate, and this electron withdrawing groups are mainly found on the reduced position of the product. Let's take the example of benzoic acid. This COOH group is electron withdrawing group and it increases the reaction rate. And in the products, when we see the products, then the major product is one at which the COOH group is present at the reduced position. This is the position at which reduction has taken place. So this is the major product. This takes place through a general fact, a fact that you have to keep in mind. It is a general principle that electron donating groups promotes ortho and meta reduction. Electron donating groups such as OCH3, they facilitate the ortho and meta reduction. See here, the reduction has taken place at ortho and meta position, while the electron withdrawing groups promote ipso and para reduction. This is the electron withdrawing group and it promotes, this is the ipso position. Ipso position is one when two substituents share a position. here COOH along with the H group. So this is ipso position and this is para position. The explanation for this is based on the distribution of electron density in the intermediate radical anion. Let's see the mechanism. This is the first step. In the first step, an electron attached to the reactant and we get a radical anion. This radical anion undergoes resonance and we get these two resonating structures. This anion gets stabilized through resonance. Electron donating groups stabilizes electron density at ortho and meta positions. This is ortho position and this is meta position. While protonation occurs at these positions only. Where the negative charge is, protonation occurs at that position. While electron withdrawing groups stabilize electron density at the ipso position, this is the ipso position and this is the para position. And later protonation occurs at these two positions and we get the product at which the reduction has occurred at ipso and at para position. आज के लेक्चर में हमने एल्काइंस और एरोमेटिक रिंग्स के रिडक्शन के बारे में बात की. नेक्स्ट जो हमारा लेक्चर होगा उसमें वी विल टॉक अबाउट रिडक्शन ऑफ एल्डिहाइड एंड कीटोन्स. थैंक यू.